Hello there, my name is Charles Msepa. Welcome to the second presentation on determining or finding eigenvalues of a given matrix. In this presentation, we're going to look at how to determine eigenvalues of a 3x3 matrix. I'm going to take one matrix of this form. Like said, the given matrix A, determine the corresponding eigenvalues. What we're going to do here, we're going to discuss two methods using the same matrix, just to show you different approach how you can deal with this type of a problem. So it will be up to you to choose which approach you feel comfortable with. So let's start by saying here's solution. So I hope it's clear to everybody that our target is to end up with a list of eigenvalues. In this case, there will be 3 eigenvalues. As you can see that the order of matrix is 3x3. So it's going to lead us to a characteristic polynomial, which is A minus lambda, a polynomial of degree 3. In this case, we're going to compute this as follows. It will be 1 minus lambda, 1 minus 2. Here we've got 1, and then 2 minus lambda, 1, 0, 1 minus lambda, 1 minus 1 minus lambda, minus 1 minus lambda, and that is a determinant. Now at this stage, I'm going to assume that everybody now knows how to compute the determinant of a 3x3, and this, if I'm not mistaken, this will take us to a cubic expression of lambda cubed minus 2 lambda squared minus lambda plus 2. So this is our characteristic polynomial. Like we said before, this is our initial step. Let's number it here 0. Now our second step, say number 1, it will be to solve the characteristic equation, which we get by equating this polynomial to 0, which means lambda cubed minus 2 lambda squared minus lambda plus 2 equals to 0. Now, in this case, this is equivalent to saying, in short, this is what the expression we wrote as lambda minus a minus lambda I determinant equal to 0. Okay. Now, having arrived at this characteristic equation, we now need to factorize it in order to get the roots of this polynomial, which will be the eigenvalues of the given matrix. Now, at this point we need now to evoke some theories of factorizing polynomials like this, and in this case we have the factor theorem, but also the theory on roots. We know that if we've got a polynomial like this where the leading coefficient is 1, we should know that the possible roots of such a polynomial are factors of the independent term, like here is 2. So then we can now express 2 in terms of Swiss vectors, which can be minus 1 multiplied by minus 2, and also 2 is 1 multiplied by 2. So we know that the factor theorem says if let's say call this polynomial p of lambda, and if we were to find such roots, the factor theorem says that if we have a number a and we've got that p of a is equals to 0, then lambda minus a is a factor of the given polynomial. So what we need to do now, we need to check these possible roots and see which one of these numbers gives us this kind of expression. Then we can create a term like this. So let's start by the simple ones. Maybe let's start by minus 1 here. If substituting it by minus 1, we're going to get minus 1 to power 3 minus 2 times minus 1 to power 2, and there we're going to have minus 1 minus 1 plus 2. Then what is this gives us that here we're going to get minus 1 because there are 3 negative signs, and they are going to get 1 times 2, which is going to be minus 2, and then here we've got 2 negative signs, we're going to get plus 1 plus 2. This gives us 0. So according to this, it means that lambda minus our a is minus 1. Minus 1 is our factor, which actually means that lambda plus 1 is a factor. So now, which means now we can use this factor to divide this polynomial, in this case using long division of polynomials, to reduce this cubic expression to a quadratic one. So let's start on that. This is one of the things which people at this stage might have forgotten, but this is a reminder. That's one way you can approach you can use to find the roots of this polynomial, which are your eigenvalues. So right here, lambda plus 1 dividing lambda cubed minus 2 lambda squared minus lambda plus 2. Now dividing by lambda, this leading term here, we get lambda squared. You can write here lambda squared, multiplying there, we get lambda cubed minus plus lambda squared. Then we subtract this from the expression there. We subtract here, we get 0. This signs become negative. Minus 2 minus lambda cubed minus 2 lambda squared minus lambda. That will give us minus 3 lambda squared. We bring this one down as minus lambda. Then we divide again this leading term here by lambda. We get minus 3 lambda. Multiplying there, we get minus 3 lambda squared minus 3 lambda. We again subtract here. We get 0 here. Now we get plus 3 lambda here minus lambda. We get 2 lambda. Bringing these 2 down with that. Next thing we do, we divide again the leading term here. We get plus 2, then multiplying we get 2 lambda plus 2. Now subtracting here, we can see that we get the remainder 0, which actually confirms that this is a factor of the polynomial. So what we can do now, we rewrite the equation, the characteristic equation as lambda plus 1 multiplied by lambda squared minus 3 lambda plus 2 equals to 0, where we can see that this quadratic expression is factorizable, and then we write this as equals to lambda plus 1, and this can be factorized as lambda minus 1 by lambda minus 2, and this being equal to 0, we can now conclude that the zeros of the polynomials there are, can say now, therefore taking from this being equal to 0, lambda 1, our first eigenvalue is minus 1, lambda 2 is equals to 1, and lambda 3 is equals to 2. So there we are. We've got 3 eigenvalues, minus 1, 1, and 3. So what was important in this approach, I think this helped us to revise how we can factorize polynomials using the factor theorem and some theories of factorizing, theories on rational roots of polynomials. So now at this stage, I think this is one approach. I'm going to take again this exactly the same example, the same matrix, and use a different approach, which some of you might find easier or challenging. So it's up to you, to be up to at the end what you want to do. So the next example, the next approach, let's take the matrix and let's say alternative approach. We've got the matrix there given. So what I'm going to do here, we'll start exactly at the same point. That is, our starting point will be A minus lambda I determinant equals to 1 minus lambda 1, 2, then minus 1, 2 minus lambda 1, 0, 1, minus 1 minus lambda. So this approach actually consists in using properties of determinants and row and column manipulations. So what we know is that as a property of determinants, that if we decide to add 2 columns or 2 rows to produce a new column within matrix, the determinant does not change. In this case, what we decide to do, let's rewrite equivalent determinant using properties of determinants. Let's say here we add column 1 and column 3 to produce a new column 3. That kind of transformation will not change the determinant. So what we're going to have here, we take this we take column 1, we add it to column 3, which is this one. And then what we're going to get here, we're going to get, let's first of all copy column 1. Sorry, there's a mistake. This is -2. If we take column 1 as it is, -1, sorry, 1 minus lambda, -1, 0, and then we give 1, 2 minus lambda, 1. Now the new column 3 is a result of this operation. Then we say -2 plus this column, we're going to have -1 minus lambda. So we're adding this entry and that entry. Coming this side, adding this entry and that entry to be 1, that we get a 0, to be 1 from this row 3 plus -1, we get a 0 there. Then here adding this entry and that 0, we get the same entry, -1 minus lambda and that. So emphasis that this kind of column, like combination of columns, will not alter the determinant. And then another property we're going to use for determinants, property of determinants we're going to use is that if we're calculating a determinant of a matrix like this and we multiply a row or a column by a scalar lambda, the determinant will come as a lambda multiple of the determinant of the original matrix. So what we're going to do here, we're going to look at this last row here and see that there's a common factor which is a -1 minus lambda. So then we can take it out as a common factor, -1 minus lambda. Then we've got here 1 minus lambda, -1, 0, 1, 2 minus lambda, 1, and then we're going to have 1 there, 0, and 1. Then we've got the determinant there. So that is by factorizing, taking a common factor, -1 minus lambda. So then the determinant is going to be this same. Now, coming up here, we're going to have minus lambda -1 minus lambda. Then we apply another property of determinants to this matrix. In this case, what we're going to do, we're going to use rows 1, subtract row 3 to get our new row 1. So to get our new row 1. Again, this kind of operation will not alter this determinant. So if we do that, if we say 0 plus lambda, 1 minus lambda, we're going to have minus 1 minus lambda minus 0, we're going to have 1 minus lambda there. Then 1 minus 1, we're going to have 0 there. 1 minus 1, we're going to have another 0 there. Then we leave the rest of the rows as they were. 2 minus lambda 0, 0, 1, 1. So what we should see is that this actually simplifies the determinant we're going to calculate here. So next, what we can do now, we can use our very first method, or even if we want to use cofactors and minors, it will be easier to use this row which has got 2 zeros, which means we're going to drop the first row and then the first column, and we get the determinant just going to one calculation. Or otherwise, we can just multiply the diagonals, and then if we multiply this diagonal, the only diagonal gives us non-zero product is the principal diagonal. Otherwise, this way, that and that will be 0, this one and that will be 0. Along the secondary parallels, we get the 0, 0, 0, 0, 0. So the determinant of this is going to be minus 1 minus lambda multiplied by 1 minus lambda multiplied by 2 minus lambda multiplied by 1. So this is our characteristic polynomial. So in the second step, our step number 1, this is our initial step. One day we set up the equation minus 1 minus lambda multiplied by 1 minus lambda multiplied by 2 minus lambda is equals to 0. Now, again, we can see that this will take us to fact that minus 1 minus lambda is equals to 0, or 1 minus lambda is equals to 0, or 2 minus lambda is equals to 0, which actually, from which we can conclude that lambda 1 is equals to minus 1, lambda 2 is equals to 1, and the lambda 3 is equals to 2, like exactly what before. So at this point, I think when it is now clear what are the two, this is an example of two approaches we can use to find our characteristic, to find our eigenvalues. First of all, we can factorize the polynomials the usual way we did, or we can use the properties of determinants in this approach. In this case, you need to revise your theory on properties of determinants and recap also how to operate with rows and columns in order to perform this task of finding eigenvalues. I think at this point, I would like to say thank you for listening. You can take two approaches and the practice, whichever suits you is fine, as long as you arrived at the correct values of eigenvalues. Bye for now. See you in the next presentation.